Hi everyone, welcome to the lesson video for section 3.6. Today we're going to be learning about solving systems using matrices. And our objectives are that we can represent a system of linear equations with a matrix and then go from there and actually solve a system of linear equations with matrices. So as always, let's begin by defining our key word, which today is matrix. A matrix is a rectangular array of numbers, and we usually display a matrix within brackets. When we're talking about the dimensions or the size of a matrix, we name the number of rows by the number of columns. So you can see in the example below, we have matrix A. There are 2 rows and 3 columns of data values, and we call this a 2 by 3 matrix. So we can write it as A or A sub 2 by 3. All of the numbers within the matrix are called elements of the matrix, and we identify the elements by its row and column numbers. So now I'd like to show you how to name each of the elements in the example matrix A that we have above. So like I said, we name each element by its row and column number. So I labeled right here, the first row is A1, and the second row is A2. So you can see in the beginning of each of the subscripts, for the first row we have a 1, and for the second row we have a 2 in front. And then after you list the row number, you list the column number of each term. So you can see in the first term we have A11, that's because it's in the first row in the first column. And then in the second term we have A12 or A sub 12, and that is row 1 and column 2, etc. So now I'm just going to rewrite all of the terms of the matrix from above and name them with each of their corresponding row and column numbers. So based off of the matrix A that we have above, the first term A sub 11 is equal to 2, A sub 12 is equal to 4, A sub 13 is equal to 1. You could also name them by saying A row 1 column 1 equals 2, A row 1 column 2 equals 4, A1 row 1 column 3 equals 1, etc. In example 1, we're going to have another opportunity to learn how to name elements in a matrix. So take a moment to jot down this new matrix A. The size of this matrix would be a 3 by 4 because it has 3 rows and 4 columns. So in this example, we need to take a look at this matrix and tell what the element A sub 23 is equal to. And you may be wondering to yourself, does the order of the subscripts matter? And the answer to that is yes, the order does matter. Because if you said A sub 23 and A sub 32, those would be 2 different elements in the matrix. A sub 23 is row 2 and column 3 versus A sub 32 is the third row and the second column, which are different numbers. So when they're asking for us to name the element in the second row in the third column, what you really want to do is just figure out what number is in the intersection of the second row and the third column. So you can see right here that they nicely highlight it for us, and hopefully it's obvious to you that that term is the number 8 because that's where the second row and the third column intersect. Just to prove the point of how we were talking about before, the order does matter. If you by chance named the term that was in the third row and the second column, that would actually be the number -2, which is a different element than the one that we just named. Now we're going to learn how to write systems of equations in matrix form, and then after that we're going to learn how to solve them using matrices. Okay, so here I'm going to show you how to represent a system of equations with a matrix. Before you start writing down these 3 bullet points, I encourage you to take a look at the system of equations that we have below. So we have x plus 3y equals 7 and 3x plus y equals -8. What we do is we take the coefficients of the 2 or more variables, in this case we only have 2 variables in each equation, and you take those coefficients and you drop them down into the matrix. So the first pair of coefficients. So we have in front of the x, we have a 1 and a 3. So you can see 1 and 3 in the first column of the matrix. And then the coefficients in front of the y are 3 and 1 respectively. So you have 3 and 1 in the matrix. And then whatever the equations are equal to, those constants are in the last column of the matrix. So take a moment to jot down the system of equations that I just talked about and the corresponding matrix that it transforms into. And just to remind you, if you see a variable with no coefficient in front, we assume that we're multiplying by 1. So that's where those ones are coming from. And then you want to draw a vertical bar to replace the equal signs and separate the coefficients from the constants. That's what you do in the matrix. So like we were just talking about, each matrix row represents an equation. The last column shows the constant to the right of the equal sign, and each of the other columns show the coefficients of one of the variables in the equations. In example 2, we're given two different systems of equations. Part A only has 2 linear equations and Part B has 3 linear equations. We're going to learn how to take these systems and put them into matrix form. So you can see in part A that we have the system 2x plus y equals 9 and x minus 6y equals negative 1. Before I turn this into matrix form, I'm going to put a 1 in front of the two variables that do not have a coefficient listed. As we talked about before, we are multiplying by a 1. Now what we want to do is take those coefficients. So the first row is going to be 2, 1, and 9. And the second row is going to be 1, negative 6, and negative 1. You can see that I'm including the minus sign and the negative sign, dropping those down. The order of the elements is important in this matrix because if we changed up the order, then we would be changing up the system of equations and we'd be solving a different system. And then what you want to do is put brackets around. And like I said before, you want to put a vertical bar to replace the equal sign and separate the coefficients from the constants. So that's how you take that system of 2 equations and put it into matrix form. In part B, it's very similar, except this time we have 3 different equations. Before making it into matrix form, I'm going to rewrite it so that the x, the y, and the z variables are all lined up. That'll make it easier. So as you can see, I am writing each equation in the same variable order, and you want to line up the variables. So the first equation is identical because the x, y, and z were in order. The second equation didn't have a y, so you can choose to either leave a blank space here or put a 0y. I typically like to put zeros because that actually helps me remember that there's going to be a 0 in the matrix there. And then the rest of that equation is the same, plus 3z equals 12. The last one's the most different from the original. So the original was y equals negative 5x plus 1. So what I did was I added 5x to the other side, so I have 5x on the left side now. I put a 1 in front of that y, because as we talked about earlier, there's a 1 in front. There's no z, so I put a plus 0z, and then I kept 1 on the right side. So now you can see the variables x, y, and z are lined up nicely, and that will make it easy for us to change it into matrix form. Make sure you also put 1s in front of any of the variables that don't have coefficients listed. Now what we want to do is, of course, rewrite these coefficients and constants and bring them down. So the first row is going to be 1, negative 3, 1, and 6. The second row is going to be 1, 0, 3, and 12. And the third row is going to be 5, 1, 0, 1. And then just make sure you draw that vertical bar again to separate the coefficients from the constants. So you can see that when we have a system of 2 equations, we have a 2 by 3 matrix, and for a system of 3 equations, we have a 3 by 4 matrix. In example 3, we're given a matrix, and what we need to do is write the linear system of equations that this matrix represents. So this is actually the exact opposite, or vice versa, of the example that we just completed. So remember that each row shows the coefficient and constant of one equation. So what I want to do is rewrite the first row with some spaces. And since there the size is a 2 by 3, that means we have two equations. So that means if there's two equations, there's two unknowns, or two variables. So I'm going to attach x to the 5 and y to the 2. And since there's no negatives involved, I know that this is going to be a plus, and then that vertical bar represents the equal sign. So that means the first row, which was 5, 2, and 7, is now the linear equation 5x plus 2y equals 7. The next one's really similar, so 0x plus 1y equals 9. So this is the system of linear equations that this matrix represents. And you may be thinking to yourself, do we need to solve this? Well, the problem doesn't ask for us to do that, but we can actually solve it pretty easily because we're actually given one of the variables, y equals 9. So to solve this, we just need to find the x. And you're probably thinking to yourself, oh, I just plug in that 9 for the y in the first equation, and you are correct. So let's do that. So we get 5x plus 18 equals 7. Subtract 18 from both sides. So we get 5x equals negative 11. Divide both sides by 5. And we find out that x is equal to negative 11 fifths. And that's equal to 2.2, negative 2.2 in decimal form. So the solution of this system of linear equations, or this matrix, is the coordinate point negative 2.2, comma 9. Next up, I'm going to show you how to solve a system using a matrix where we do not have to put it back into the equation form. We're actually going to keep it in the matrix form. The good news is that when we solve a system using a matrix, we actually use the steps that we used when we solve a system by using elimination. And in my experience, a lot of people prefer elimination over substitution, so that is good news indeed. And each step that we use when solving the system in the matrix form is called a row operation. And when we perform these row operations, our goal is to get the matrix in this form where there are ones on the diagonal and zeros everywhere else. So you can see right here we have 1, 0, 0, 1, and then the vertical bar A, B. So that would translate into 1x plus 0y equals A, and 0x plus 1y equals b. The good thing about the zeros is that they basically just take away that other variable. So we find out that x equals a and y equals b. That will make more sense once we have numbers in the a and the b spot. And then similarly, this was a system of 2 linear equations. This next matrix is actually a system of 3 linear equations because we have a matrix that's in the size 3 by 4. So to change this into equation form, it would be 1x plus 0y plus 0z equals a, 0x plus 1y plus 0z equals b, and 0x plus 0y plus 1z equals c. And all the zeros cancel out. So we find out that x is equal to a, y is equal to b, and z is equal to c. So like I said before, the size of the matrix shows you how many equations you're dealing with. And for the first one, we had a 2 by 3 matrix, and the second one, we're having a 3 by 4. In the key concept box, we have the 3 typical row operations that we perform when dealing with matrices. The first one is when we just switch any 2 rows, so that literally means just swap places with the rows. So you can see that the first row became the second row and vice versa. The second row operation that's typical that we see is multiplying a row by a constant. So you can see in the second row here, we are multiplying the second row by 2. So we're just doubling all the values. The first row stayed the same in this case. The last possibility is when we add one row to the other. So you can see that the second row is staying the same here, but we're actually adding the first row and the second row to change the first row to become 7, 0, and 11. So those are the 3 possible row operations that we typically deal with, and it is possible to combine any of these when we're solving a matrix. In example 4, we are about to learn how to solve a system using a matrix. So first of all, we want to rewrite our equations in matrix form. So remember, the x has a 1 in front. So we have 1, 4, -1, and 2, 5, 4. And then draw the vertical bar where the equal sign was. So what we want to do is get our matrix into this form right here in the top right. And we saw this earlier where we have a 1, 0, and a 0, 1. This is called the identity matrix, and the identity matrix makes it really easy to solve from there. So first step is we want to get a 0 in this spot right here, the second row, first column. So in that spot right now we have a 2. So what we need to do is think to ourselves, how can we make that 2 a 0? You may think to yourself, well, why don't we just multiply by 0 to the whole row? Well, if we multiply by 0, then that makes every element in the row 0, which eliminates the equation completely. So we don't want to do that. What we want to do is multiply the first row by -2 and then add that to the second row. Remember that this is very similar to elimination that we practiced in the previous couple sections. We use the same steps, but the variables don't appear in the matrices. So what I did was I multiplied the first row by -2, so I have the new values -2, -8, and 2, and now I'm going to add. The reason why I'm adding is because I want to cancel out the first column. So when we add, we just get a 0, and then when we add in the middle column, we get -3, and we add the last column, we get 6. So these are the new values for the second row. So now we have a 0 in the bottom left-hand corner, which was our first goal. Our second goal is to make this -3 in the bottom right-hand corner a +1. So get a 1 in the second row, second column. And the way that we can get a 1 there is by multiplying by the reciprocal. So the reciprocal of -3 over 1 is -1 over 3. So we're going to multiply the second row by -1/3. When we multiply by -1/3, we get the new values of 0, 1, and -2. So this is our new second row. Our third goal is to get a 0 in the first row, second column position. So in the 4 spot, that 4 needs to become a 1. Now we can't just multiply by the reciprocal here, because if we multiply by 1/4, then we're multiplying everything in the first row by 1/4, which changes that 1 in the beginning to 1/4, which is definitely what we don't want to happen. So instead what we want to do is multiply the second row by -4, and then add that to row 1. So when we add those two, we get 1, 0, and 7. That is our new row 1. So now let's rewrite our new matrix. So now you can see we have the identity form of 1, 0, 0, 1. So the numbers on the right side of the vertical bar are the solutions of the system. So the solution is the coordinate 7, -2, because the first row is the x value and the second row is the y value. So that's where those two lines intersect. And of course, to check your answers, you could plug both of those coordinates, or the 7 for the x and the -2 for the y, back into the original equations, and they will work when you plug them back in. This matrix that we ended up with in the last example is in the form that we call reduced row echelon form. And that's because it represents the solution of the system, where we have 1s in the diagonal and 0s everywhere else. And this reduced row echelon form actually makes it really easy to solve matrices that are bigger than a 2×3. So I know what you're thinking. Do we really have to do bigger systems by hand? And the answer is no. The good news that I have for you is that on your graphing calculator, there is a button called Reduced Row Echelon Form, or abbreviated it would be RREF. And that actually does all of the row operations for you. So the process that we just went through, I show that to you because I want you to be familiar with what the calculator is doing when we use this operation. So now in the last example, I'm going to teach you how to use this RREF button. So in example 5, we have a system of 3 equations. And you can see that the variables are already lined up. There's just one variable missing, so I'm just going to put a 0b in that spot. So when we type this into the calculator, there will be a 0 in that position. Okay, so now what you want to do is grab your graphing calculator and turn it on. Before we type in our matrix into the calculator, I want to make sure that we all understand that this size of the matrix is 3 by 4 because there are 3 rows and 4 columns. So take a moment to write down this matrix. I just took the coefficients and the constants and we practiced this skill earlier, so hopefully you agree with the matrix. Now in the calculator, what we want to do is go to second matrix. So we just went to second matrix, and then now arrow over to edit and press enter. And the size is always going to ask you what the size of the matrix that you're dealing with is. So we're going to type in 3 by 4. So it makes the matrix for us. Now what we want to do is type in all the values. So let's start with the first row. 2, enter, 3, enter, -1, enter, and 1. And I'm going to keep going. So the second row is -4, enter, 9, enter, 2, enter, 8, enter, and -2, enter, 0, enter, 2, enter, and 3, enter. So feel free to pause here if you need to catch up and type in your numbers into the matrix. So to exit out of the screen, you want to press second quit. And now we're going to go back to matrix, so second matrix. And we want to use the reduced row echelon form button. So you want to go over to math and then arrow down until you see RREF and press enter. And now what we want to do is just input the matrix that we just typed in, and we labeled it as matrix A. So go back to second matrix. And you can see right there that we have the 3 by 4 matrix entered, so press enter because it's highlighted on the matrix A. And press enter again. And you can see that it put the first 3 columns in reduced row echelon form, the identity form. So you can see ones on the columns, on the diagonal actually, and then zeros everywhere else. And you can see some decimals over there. Those are actually the solutions of the system of equations. And we want to change that 0.66 repeating into fraction form. So you want to go to math, fraction is already highlighted, press enter again, and now it changes our matrix into fraction form. So the numbers in the last column are the solutions for the variables a, b, and c. So our solution is a equals 1/2, b equals 2/3, and c equals 2. So those are the values of a, b, and c that satisfy all 3 equations. And like we talked about earlier, you can check your answer by substituting your values for a, b, and c back into all 3 equations, and you'll see that they are satisfied. Here's our lesson check for today. So please make sure you complete these problems, and let me know if you have any questions the next time we see each other.